All right, now that we've figured out how to read a calendar, let us go back to the original course plan, which apparently was reasonable. What was unreasonable is that announcement I most recently sent, right? So I will delete that, and Hannah, you can delete it from your email too. And we're going to stick with the original plan for Quiz 2, Review Day 2, and Test 2. All right? And you have about a week, a little bit more than a week to finish Mission 3. That should be plenty. Mission 3 is pretty long, all right? It's about like 9 pages, but once you've worked all those problems, you should pretty well understand the material. I do think you really should do, recommended homework in addition, I don't think that mission is really sufficient for you to learn all the material, but I don't want to make you turn in anything beyond that either. So it's kind of up to you to do more of the recommended homework problems. Now, my brother is also a math professor, and so when he tells students that homework is recommended but not collected, he usually has students say something like, "You mean it's not for a grade? You're not going to collect it? It's just recommended?" And he's like, "Yeah, it's just recommended. Like I recommend that you pass this class. Passing the class is optional, which is not something I say because I don't have tenure, but it is actually good advice. I mean, you should do some of the recommended homework at least. If you don't have a way to do that, you should come and talk to me. I do have, the textbook. You can take pictures of the problem sheets if you want in my office hours or whatever. All right, so let's get back into it. I'm going to start you with an example. So I'm going to say let f of x equal to 1 over, let's say 2x plus 13, and let g of x equal to the square root of x squared plus 8. All right? I want you guys to calculate the formula for f times g of x. I want you to calculate the formula for g times f of x. And I also want you to calculate the formula for f composed with g of x. And I also want you to calculate the formula for g composed with f of x. So I want you to work out all those things. I'll give you a minute. While we're having that minute, I'm going to complain about Monday. So first of all, I had the awesome plan to go down the end of this week. Then I was going to go back and visit my mom on the way back. It was a fantastic plan, but no. What happened? Realtor's texted me Friday, "Congratulations on your closing." But the thing is, my closing was supposed to be the Friday at the end of this week. So this is disconcerting, yes? So I called the closing company. Closing company calls me in my office. I'm, working on solutions Friday afternoon. I'm like, "What? My closing is at 4 today?" "Yeah, I'm in Alabama. My previous house is in Virginia, right? I don't know about you. I personally do not own a car that can get from here at 1 o'clock to Virginia at 4 o'clock, right? I mean, I don't know if that car exists. Maybe Airwolf exists. Do you guys know Airwolf? Nobody knows Airwolf. Oh. There's this fantastic, ridiculous show about a helicopter that can go Mach speed back in the 80s. It's an amazing, ridiculous show. Anyway, long story short, I had to drive to Virginia, close my house Monday, and then I'm back. So I will be here the rest of the week. Yeah. Uh-oh. Let's see here. So let's see if you guys got the right answers here. So first of all, what is fg of x? What's that mean? This is just the product of f of x and g of x, right? And that is equal to 1 over 2x plus 13 times the square root of x to the x squared plus 8. Or if you like, you could rewrite it like this, square root of, I mean, this is not necessary, but I don't know. I'd probably leave my answer like this just as a matter of style. There you go. This is the product of the function f and the function of g. Simple as multiplying the formulas. Almost no students have a problem with this, right? We can do this. This is not a big deal. How about g times f? Well, when you multiply the formula g of x times f of x, is it different? No, right? So this is actually equal to gf of x, same answer. Because this would be technically, g of x times f of x, but that's equal to f of x times g of x because real numbers commute. So we can commute the product. Yeah? So the product of functions, it doesn't matter which order you do it in, right? How about the composite? F compose the g. So I've been piloting a kind of training wheels way of doing this, and I'm going to stick with it. Because, yep.
Over here you have 2x plus 13. Over there you have 2x plus 2.
Oh, still in the chalk. Thank you. Okay, I just forgot to take it out of the chalk. Sorry. I can explain the reason to that, but, well, anyway. I have no good reason. Oh, I know. As a mistake I made on purpose to give you guys a chance to ask that question. That was what it was. Yep. Okay, so f composed with g of x, what is this by definition? This is f of g of x, right? But a kind of sneaky way to calculate it, we can think about it as f of g. I mean, this is technically an abusive notation. It's really f of g of x, right? So anyway, what is f of g? Plug in g in the place of x, right? So that's 1 over 2 times g plus 13, right? But what is g? Well, g of x is the square root of x squared plus 8. So that's 1 over twice the square root of x squared plus 8. Close the square root, add the 13. There you go. That's the formula for f composed with g of f. Again, f composed with g is how we read that. Whereas this is the product of f and g. One more to go, right? G composed with f. What happens there? We could look at that as like g of f, right? So let's see here. That would be what? Square root of f squared plus 8. But what is f? I mean, what is f of x? F of x is 1 over 2x plus 13, right? So are these equal? Like this is this is G composed with F, right? G composed with F. Are these, what does it take for two functions to be equal? They have to be what? They have to match for every possible, they have to have the same domain, and the output has to be the same for every input, right? That's when two functions are the same, right? Are these functions the same? Well, I don't think so, right? I don't think there's any kind of, hocus pocus series of algebra steps that can get from here to there. Like, I'm pretty sure not the case. Of course, to be sure it's not the same, you could just plug in one number, right? And show that it doesn't match. If you could find one input where they don't match, then you've shown that they're not equal as functions, right? Because for two functions to be the same, they have to match at all possible inputs. So if you can even found one where it doesn't work, you've shown that they're not equal, right? Can you guys think of a function, of a value in the domain of these composites? Did I hear 0? 0 is good. So let's see, F composed with G of 0 is 1 over 2 times the square root of 8 plus 13, right? G composed with F of 0 is what? Using my formula, it's the square root of 1 over 13 squared plus 8, right? Now, I'd have to get a calculator to be absolutely sure, right? Like, what's the decimal of those? That's the nice thing about decimal form of a number, right? Is we can quickly compare whether two decimal representations are equal. When you have representations of numbers like this, it still kind of begs the question, are they equal? I don't think so, but I should really plug it in my calculator if I have it. Oops, not minus, I want plus. So I got approximately 0.0536 for F composed with G of 0. And over here, I got that this is approximately equal to 2.83. So, yeah. Okay. So the reason I'm spending so much time on this example is it's really, really important for you to come to a lasting, deep understanding that these are not the same thing. The product of two functions, we just multiply the formulas. The composite is when we take one and put it into the other, right? You multiply A times B, it's the same as multiplying B times A, right? Function products, the product of two functions commute. Composite, it's more like, you could think about function composition in terms of like putting on socks and then shoes, right? If you usually first put on your socks and then put on your shoes, right? I don't know, do people here put shoes on first and then put on socks? Because like one of these composites makes sense, and the other one's, nuts, right? Because one of these is socks then shoes, and the other one's shoes then socks. So don't take my interpretation too far, right? And I know someone in here is wearing sandals without socks and is dying to show me their feet right now. Probably. No, the other class had a person with just sandals on, and they refused to acknowledge my joke just now also. But anyway, I'm still recovering from that. They were wearing a mask, so like all I could see was the eyes. And they were glaring at me. I still don't know. All right, so anyway, this is how we compose functions, right? Now, this thing I did, full disclosure, in a proof-based math class, this could get you into trouble. It's technically an abuse of notation, right? So like if you want to be pedantic and like, you know, correct in terms of notation. What people would typically do is something like this. This is f of g of x. Let u equal g of x. And then you get f of u, and then you plug in u in the place of x, which would be what? So the other thing you could do in terms of understanding functions better, I mean, there are various tricks. Some of us need these tricks, some of us don't. It kind of depends on how you're wired. But you could replace this like it's f of a box, and that's 1 over 2 times box plus 13. So you can put whatever you want into the box. Like u could go in the box. There you go. So this is 1 over 2u plus 13. And then you put u equal to g of x, which is going to get us back to here again. Right? So I thought to myself, yes, I can introduce this extra step, let u equal g of x, right? Or I can just teach the students to take the letter g and put it into the formula and do this and avoid all the snickering about me writing f of u on the board. So, you know. Because no good comes of this. No good ever comes of this, and I never know where it's going to lead me with a given class. So anyway, you can use this notation. I don't know the math department well enough because it's, you know, like at this point I usually have had conversations with all my fellow faculty. I haven't really had that. So like I'm not sure if there's like a legalist here, you know, who's like really like, they can't write this, you know. So anyway, I will eventually get YouTube complaints about doing this. All right? I mean, it's not quite right. But, what's that? People with too much time on their hands. The question was from who? But listen, this abuse of using g instead of g of x is really part of a larger abuse which we do make in pre-calculus and calculus, which is sometimes we say this, like this is something we should talk about. And it matters because if you're not aware of it and it sneaks up on you, it can get you really, really confused. So it's a notational warning. So what is the function? See, some people would say the function is f. Like f is the function. Most often, we don't say that. In calculus and in this course, we'll say it's f of x. Right? Now, technically that's not true. The function is f. F of x is the value of the function at x. But we often identify those two things for the sake of not being too like legalistic in our language, right? And because, well, also I don't want to always be raining down condemnation on students for being like only 80% correct. I'd just rather say these two things are the same thing so that I don't always have to be correcting you about using f versus f of x, because you've been taught to confuse these two things already in your previous math classes, right? So we'll use f for the function. We'll use, say, f of x as the function. An example of this would be somebody might ask you to calculate the domain of the tangent of x next semester, right? To the legalist, this doesn't make sense because you should be asking what's the domain of tan, where tan is the function, not tan of x. Tan of x is the value of the function tangent, right? I don't think this discussion is particularly interesting, right? So I try to avoid it, but I'm just warning you it's something that's there that can sneak up on you. And the other thing is, there's another temptation, which is to think of x as multiplication by x, right? It is not multiplication by x, is it? We're feeding x into the function. It's the input. So that's another danger. But thinking of that as multiplication by x, that's a mistake I usually only see in differential equations. You guys never make that mistake. For some reason, differential equation students start making that mistake. It's because of a particular calculation we do there. Okay, so let me erase the evidence and begin our discussion of one-to-one functions. Let's talk about one-to-one, aka injective functions. So let me start us with a definition. If we have f as a function, let's say from a to b, then f is one-to-one if whenever f of a is equal to f of b, that implies that a is equal to b. I can put it in words. What a one-to-one function means that, in words, it means that outputs match only if same inputs. Oh, if inputs match, right? It's saying that if the value of the function is 3 at two different inputs, those two different inputs better not be different. They better actually be the same input. This is a one-to-one function. Let me draw a graph. So like graphically, there's an easy test. If we had a function and it looked like this, well, let me make that more dramatic a second here. If we had a function and it looked like this, right? So what I'm supposing is maybe -2 and I guess for this one too, right? F of 2 equals to f of -2, right? Whatever that value is, it could be 3, I don't know, it doesn't really matter what the value is specifically, right? So this function is not one-to-one because we have two different inputs, -2 and 2, which are both giving us the output of 3. So this would be an example of a function which is not one-to-one. Yeah? Oh, that was not a question. Okay. Wait a minute, is your hand usually up like that? Oh, okay. It's okay. It's okay. You guys are generally undistracting. I had a student in another class shave his head last week. Very distracting. Very distracting. And it's catching. Like, once he shaved his head, even though he's not there the next class, then a girl shaved her head. Like, I don't know, I'm going to go in next class, and they're just all going to be bald. Like, I don't know where it's going. I'm going to resist the urge to join you in that comment. Not where I was going with it, but it's fine. But we should go on. Okay. I would just go on that one. No. It always comes back to ending class somehow, you guys. That is what all my classes have in common. Like any discussion in class, it somehow always devolves into da-da-da-da, therefore end class. Like, sort of like, Have you ever heard the Godwin's law on the internet? Like any internet argument can devolve into a discussion of Nazis within like a certain amount. There's kind of a similar law for in-class discussions. Any in-class discussion will devolve into a discussion of like leaving class within about 3 iterations of the discussion. Like it's a law. Anyway, my point to you, what I'm trying to get to here, is graphically this one failed to be injective. I've given you the algebra that shows it's not injective, right? But graphically what the problem is we have a horizontal line that cuts through the graph in 2 points, right? So we say that this fails the horizontal line test. See that? Horizontal line test. Horizontal line intersected. More than one place. More than one point in the graph. So, you know, horizontal line test is this. If y equals to f of x only intersects horizontal lines at, I find myself writing at, goodness gracious. Curse you, English, what have you done to me? If y equals f of x only intersects each horizontal line at, dang it, I'm still back to at. At. Oh, I'll finally write it. At most one point. Then f is injective. It's 1-to-1. Can someone here write that sentence like a normal person? I don't have the words in me at the moment.
If y equals f of x only intersects.
You're like, it doesn't make sense, so you can't rewrite it. If y equals f of x only intersects each horizontal line at most one point. At only one point. At only, we'll go with only 1 point. But then I have to add more fine print. Well, the thing is, here's the problem, guys. If this is the function, like this, yeah, then what's the range? I mean, yeah, up here, I'll draw the horizontal lines like this, right? Fine. It's all good. 1 point, 1 point, 1 point, 1 point, 1 point, right? How about this horizontal line? See, that doesn't intersect the function at all. That's why I wanted to say at most 1 point, because sometimes it doesn't intersect the function at all, and that's fine, because that is a horizontal line which just falls outside the range. So this is what I was trying to communicate in my English sentence, which I failed to write correctly. I mean, I think it's logical. It's just clumsy, the wording at the moment. Shall I start over? Let's try it again. If each horizontal line intersects y equals f of x at, I'm back to it again. Dang it.
At 1 point or none.
At 1 point or none. Thank you. F is injective. So this is the so-called so injective is 1-to-1, 1-to-1 is injective. You're like, why can't we just have one word? Because that would make it too easy for the students. We need to have 2 words for everything, right? But this function passes the horizontal line test because, yeah. All right. So you could take the horizontal line test as a definition for, injectivity of functions, if you like. But let me show you. Let's look at a specific example here. Let's let f of x equal to x minus 8 quantity squared plus 10, where the domain of f is equal to, let's say, 8 to infinity. Let's show f is 1-to-1. And I'm going to do it algebraically, all right? So I'm going to use the definition I just erased. But you've already written in your notes, so we're good. So I'm going to suppose that A and B are in the domain of f, and f of A is equal to f of B. If I can now show by algebra that that forces A to be equal to B, good. Then we've shown that the function's 1-to-1. We've shown that f of A equals f of B implies A equals to B. Okay, so what is f of A? We have A minus 8 squared plus what? Plus 10 equals to B minus 8 squared plus 10, right? Thus what? A minus 8 squared equals to B minus 8 squared. And then what can we do? Take the square root of both sides, right? But when we do that, what do we have to allow for? Whenever you take the square root of an equation, you have to ask the question, if you have the square root of something squared, well, the answer is plus or minus what you started with, right? You don't believe me? Fine. It's too late. I sense disbelief. We will factor it instead. This is the difference of squares. So difference of squares we can factor. You're like, I said we do. But it's a difference of squares. We can factor it, right? I mean, you could think about the top thing is, this is basically the pattern alpha squared minus beta squared. And so what we're looking here is alpha minus beta. And this right here is alpha plus beta. That's the pattern. You're like, why'd you got to use alpha and beta? Because I already used A and B. All right, sorry. Anyway, can you clean that up? We have what? A minus B? A plus B. Because the 8's cancel. And what does that tell us? Yeah, either A equals B or A equals minus B, right? That's 2 choices. So it seems like that says that this function's not 1-to-1, right? Because a equal to minus b, that means that they're not equal, right? So, but I said we should show it's 1 to 1. So why is that second possibility not a trouble to us? What did we say at the start of this? Where a and b are taken from? The domain of the function, right? Which is what? What's the domain of the function? 8 to infinity, right? So what's that say about a and b? Right. This tells me that a and b are greater than or equal to 8, right? So this is not possible because a and b are both larger than 8. One can't be the negative of the other. So we're forced to see that they're equal, which then shows that the function's 1 to 1. So there's like one problem in your homework like this. I wanted to work it kind of slowly. The way you should do that homework problem is to take the formula, set f of a equal to f of b, and then do algebra to show that a equals to b follows from it. That's all you do. That is the algebraic way of doing the horizontal line test. Now, this you could graph, right? Why does the algebra work out like it just did? So we're going over 8, right? And up 10, basically. We're here. So if we just looked at y equals f of x without any strings attached, x minus 8 squared, right? That would be all of this, right? But what did we say? We said that the domain of f was 8 to infinity, right? So what that means is we've just deleted all of that, right? So the function here is just, the graph of it's just like this, right? So when we think about the horizontal line test, we're fine because we're just cutting through the right branch of the parabola. And that's why we were able to show it's 1 to 1. Okay? So that brings me to our next definition, which is that if f is going from, say, a to b is 1 to 1, and b equals to the range of f, then f inverse is a mapping from b to a defined by f inverse of y equals to x if and only if f of x equals to y. Now I'm going to write a slightly different definition like next class, but just for the sake of the last minute here, I just want to talk about why this definition makes sense. So what do we need for a function to be single valued? We need a function to be single. Let me answer my question. We need a function to be single valued, right? So f inverse of y has to be a single value, right? Why is f inverse of y a single value in this definition in the current context? What did we assume about the function? 1 to 1, right? That's exactly what we need to be sure that there's only one input which maps to that output y, right? So 1 to 1 functions are the ones for which we can find the inverse of, right? And like next class, I will tell you about, I'll write the definition again, I'll write it more carefully. We'll look at what the graph of the inverse function looks like relative to the graph of the function, provided that the function has an inverse, right? If the function is not 1 to 1, it doesn't have an inverse. At least not without taking the domain and like chopping it down and making it smaller. You do that next semester in pre-calculus trigonometry. You'll talk about inverse functions for like sine, cosine, which is weird because those don't pass the horizontal line test. So actually there the concept is what's called a local inverse, but I'll leave that for next semester. So next time we'll talk about how to calculate the formula for an inverse function and get into all that. All right? So thanks, guys. You got it?